Hey everybody, thought I'd do a short lecture on the concepts of correlation and regression. These are a couple of tools that are pretty central to a lot of investigations, a lot of studies, observational surveys, studies like that, where we're just kind of looking for patterns and trying to investigate what's out there before we go dive in and run experiments. But again, we've been working with hypothesis testing, and these are just hypothesis tests. So a couple things that we've touched on. XKCD is amazing. Um, and hopefully this cartoon will make a little more sense as we go through today. Um, and if you're interested, this guy, Tyler Vigen, or Vegan, he has done some really amazing correlations between variables that are absolutely not related in any way. And we'll get to see why that's really interesting and why correlation can be dangerous. The biggest thing that we can understand about these ideas, this correlation versus regression idea, is that one implies causation and one does not. When we say two things are correlated, they change in ways that mirror each other, but that doesn't mean that one causes another. Again, XKCD comes through in a big way, and just kind of take a look at that one and let it simmer in your brain. At its core, both correlation and regression work with similar numbers and similar types of math. So with correlation and regression, we're working with two continuous numeric variables. I guess you could also call these discrete numeric variables, but it's some measured value and some measured value, not categorical. Now, just to shout out to the gal who made this figure, this is actually my wife's master's degree down at Moss Landing, studying this little fellow right here, the Platyrhinoides triceriata, the thornback ray. But what Kelly was looking at was relationships between different tissues, like whether it be female tissues, embryo, yolk, muscle, liver tissues, looking at relationships between mother and embryo, and to see if there was patterns in mercury or heavy metal contamination transfer from mother to embryo. And so what she did was took a lot of her continuous variables, mercury or tissue concentrations that she measured in tissues, and compared those to different tissues, and to see if relationships existed. And if you'll take a peek, she found these are what we'd call positive relationships. We see as female muscle or female tissue concentration of mercury goes up, we also see an increase in the embryo ova mercury concentration. And we have an R squared value of 0.84 and R squared value of 0.94. And this we'll get into a little in a few slides what this R squared value means, but basically it's a measure of how confident or how much of your data that line explains. And 0.84 and 0.94 in ecological terms is almost unprecedented. I was quite jealous when she popped these out. But we can look at this one graph and kind of ask almost two different questions. If we're talking about a correlation, the question we would ask is, do female and embryo mercury concentrations change in similar ways? So as one goes up, does the other go up? And does one go down, does the other go down? Or is it inverse? Whereas a regression implies some sort of change or some sort of cause. So does a change in female mercury concentration predict or cause a change in embryo mercury concentration? And this data, her work was published here in 2017 in Science of the Total Environment, if you're curious. So those are two seeming fairly similar questions with a couple key words, and it's mostly that that idea of a prediction or something causing a change that stands regression alone. And we'll see there is a measure of that prediction of change that we can calculate using the slope of our line, which is something we don't do with a correlation. This may come as no surprise at this point, but correlation and regression analyses have a set of assumptions. We need to have guidelines for our data so that we can be confident in the math we're running. And this is the same type of assumptions that we've been working with for all of our hypothesis tests up to this point. So again, with correlation, you need to have a random sample. Whatever it is, you've randomly sampled your population. Because we're working with two numeric, whether discrete or continuous variables, the other two assumptions are kind of interesting. So we're assuming that x is normally distributed, meaning has equal variance and standard deviation for all values of y. So here for each of these x values, there is going to be some sort of distribution on the y-axis. All right, and there's going to be density and a histogram that we can plot for each of those x values. And conversely, y is going to be normally distributed here on the y-axis with equal variance for all values of x. So it's kind of like this two-way histogram, or this, I guess it'd be like a three-dimensional histogram. And with a correlation, like I said, where correlation looks for similarities in patterns. This doesn't necessarily have to be, this isn't one causing another thing, but it's just a similarity in pattern. Do these two variables change in predictable ways with each other? And that predictability is called our correlation coefficient. And with a correlation, we call this rho, or that Greek letter is rho. And the estimate of that correlation coefficient, like the line of best fit, or how much that line fits your data, is our R. So you can have a rho, a negative rho. So you have a negative relationship. As one goes up, the other comes down. You can have a positive rho, and where one goes up, the other goes up. And you can see when you have a row of 1, each of those dots, each of the data points is exactly on this line of best fit, indicating that this explains all of your data. You can have row values that are less than, in between 0 and 1, or 0 and negative 1. And all that means is you may still have a positive or a negative relationship. It just means that your data are no longer as well described by that line. And if we have a row of 0, it means there is no correlation between the two variables that we were looking at. So here you can see you have a very dispersed data field and no relationship between them. So a couple things to keep in mind when you are working with correlations is you can have values between -1 and 1, and that -1 or 1 value tells you the slope of how steep your line is. Whereas the R² value, the coefficient of determination, is an indication of how much of your data is explained or predicted by the other. So if you have a very high R², like Kelly had, say R² of 0.94, that's basically saying 94% of her data was described by that correlation. And that's quite high. In ecological settings, like in my world, R² values of 0.3 and 0.4 are pretty amazing. If you can explain 30 or 40% of your data with a model, then you're doing pretty well. Whereas if you're working in an analytical, like say an analytical chemistry setting, which you do for lab work, analyzing chemicals, and you're running standards, and you need to know, if you're looking at fluorescence, amount of light emitted, and what that amount of light means for chemical concentration, your R² need to be 0.99, 0.999, basically 1. So let's take an example. We want to know, Drosophila melanogaster is a solid model organism. We use it for lots of different studies. And what we want to know is, are the effects of new mutations within Drosophila that impact the mating success and productivity, are those two correlated? Are those mutations correlated? And this idea of productivity, in case we've all forgotten from BIOL340 and 206, is just a combined fecundity, like number of offspring created, and the overall um, survival and success of those offspring. Like, so how many you have compared to how many survive to adulthood. And with two continuous variables, like you have plotted these before, we did these early on. These are scatter plots. Um, so if we take a look at the productivity right here and the overall mating success um, on the y-axis, we see a spread of our data. And the productivity, whatever variables you're working with, the ranges are going to be different. But you can look at a correlation between variables that have different ranges. As you can see, we're going from negative 0.2 to 1 and negative 2.5 to 1. Um, so when we're working with this, and working with any example, you can take these two variables, plot them together, and see if there is a relationship. It's up to you as the scientist or the researcher, whoever, to make assumptions and statements about whether that is a reasonable correlation to make. Because it theoretically is reasonable to assume that any change in productivity is going to be correlated to a change in mating success. Because the more matings that you have, the more productive you will be, possibly. Um, but it maybe not be so prudent to take a look at productivity and number of TVs produced by the United States. Um, those two things are not even closely related and therefore don't need any correlation. So behind all this, before you get to plotting your data, it's always good to start with a couple hypotheses. And again, this comes from thinking about what you expect to see, going out and testing it, and then reporting on what you saw. And these, like we have talked about, this is something you set your hypotheses before you go do your study. With correlation, what we're saying is the mating success and productivity are not related. That there is no relationship, that there's no predictable relationship between those two variables. And this gives us a row of 0. Like we saw, this very dispersed field. And like with our other hypothesis tests, the alternative hypothesis to this is basically that rho is not 0. So anything else besides rho being 0 would force an alternative hypothesis. And that anything other than rho equals 0 is saying that mating successes and productivity are correlated in some way. This is a two-tailed type of test because we're not saying mating success is positively or negatively correlated with productivity. We're just saying they are correlated. And if you want to break it down and just think about these hypotheses in general, we can use HO, H naught, and HA in the same way. You can have a rho equals 0 or rho is not equal to 0 for your statistical hypotheses. And you can just input your two numeric variables into the sentences above to come up with your biological hypotheses. One thing that I have kind of alluded to a couple times throughout the quarter is that we have assumptions for our tests, and we try not to violate them. But if we do violate said assumptions of like a t-test or a correlation, there are ways around it, and not all is lost, which is really helpful. If you are able to hold to all your assumptions, you get to run a Pearson's correlation. And this type of correlation assumes all data are normally distributed, random, and all that. And if you do violate assumptions, and this is not something that we are going to be working with much, you do a Spearman's rank correlation. And this takes all of your data and puts it in, basically gives it a rank from 1 to however many data points you have, and takes that and then runs a correlation on those rankings. And this is great because it takes away the need to have so many assumptions. So if you violate normality or equivariance or randomosity, then you can run this. And yeah, we try not to assume too much because bad things happen when we assume. So just a real brief rundown of how this works in R. So this is just another another function. This is the core function, or the core.test function. So with core, you can put in x and y, your two variables, and then indicate the method of correlation that you want. Whether you want to do a Pearson's if you managed to meet all your assumptions, or a Spearman, or a Kendall if you violated some assumptions. And with core.test down below, you can specify a number of tails with alternative. You can talk about the confidence interval, and a couple other factors if you feel like investigating those in lab. So that's the basics of correlation, and the fact that we're looking at, do these two variables change in predictable ways? Whereas a regression is slightly different in that it is dealing with some sort of prediction. So as we see, as x changes, as x increases or decreases, that is going to predict that y is going to do this other thing. And this assumes, so what we're working with today, and in this class specifically, are linear regressions. And the biggest thing here is that we're assuming that these two variables are linear related, that a line is going to describe these data. And know that this is not the case for a lot of data sets. So here we've got a set of 3 different correlations or regressions. And again, like the math, the graphs can look the same and the math can be the same, but the assumptions can be the assumptions and the conclusions that you make based on these can be very the same, very much different. So here on this side, we have 2 different levels of correlation. So you've got a R of 1 and an R of 0.6, but same slope. So here we've got 2 different levels of correlation, but these linear regressions are the same. These predictors of these variables are the same. On the right side, we've got 2 R squared values that are the same. So same amount of data are explained by these lines in these 2 models. The only thing that's changed is the slope, or this predictor. So in this one, any change in x is going to predict a change in y, whereas over here, any change in x is going to predict a greater change in y. Yep, hypotheses again. So again, we have H0 and a HA. And unlike with the correlation hypotheses, we're saying, okay, either the correlation not null hypothesis is rho equals 0, or rho does not equal 0. Here, we're looking at beta, or we're looking at the slope of this relationship. And this is saying, H0 is saying that there is no linear relationship. There is no beta, or beta equals it. There is no slope to this line. And the alternative hypothesis is saying that, yes, there is a linear relationship, and that the slope is not equal to 0. So again, assumptions, pretty simple you've seen these, again, random sample and normal distribution of data with equal variance for y across all values of x. Again, like this 3-dimensional histogram, just keeping things equal variance. We all know that means at this point you can either run a Bartlett's test, or as long as you're within an order of magnitude of each other. Hopefully this equation is something y'all have seen many times. Basically y equals mx plus b, or y equals alpha plus beta. In this case, with the regression analysis, the hypotheses were concerning beta, or were concerning the slope. And the way we use these is this. You have a slope and an intercept. And if you have a positive slope, you have a line that goes up from left to right. If you have a negative slope or a negative beta, you have a line that goes down from left to right. And depending on your intercept, you can have the same slope, but the lines just intersect the y-axis at different places. And each of these indicates potentially interesting biological patterns, like things like this, where you have 2 different lines that are changing at the same rate, but mirror each other in different magnitudes or different quantities is really interesting ecologically because you have similarities of pattern just in different situations. And then up here, this is our null. We're saying there is no slope to this line. There's no relationship here. So when we go to explain these lines and how we get to beta and how we get to our R squareds, we're looking at how well each data point is represented by that line or by that linear relationship. And we do this by plotting and understanding what the residual difference is for each data point. So if you look over here, like we've got this y caret, this is this mean here. This line represents a mean that we've calculated, this mean value and this mean slope. And as we can see, there is like maybe, okay, this white dot is the only data point that is actually on that line, that is actually on that regression. And so therefore it is 100% explained by our regression line. That's rarely going to be the case. So what we're concerned with is how far from that line each of our data points is. If each of our data points is close to our line, then this difference is going to be small. Our residual is going to be small. And the smaller our residuals, the better our line explains our data. As these residuals start to get bigger and bigger and bigger, the more dispersed our data is, and the more fuzzy our outcomes and our confidence becomes in our regression. The other important thing about residuals and understanding their relationship is that while we know it's necessary to have equal variance in running ANOVAs and t-tests and things like that, it's important to have equal residuals throughout your data set as well. This basically is the same thing as variance. And it says that, okay, there might be the residuals might be large, relatively large to whatever, but at least they're the same. We have a similar spread around this line. Whereas if we start to see like shrinking residuals or increasing residuals, that lends itself to concern on our part as statisticians. So to illustrate that, this is how you can use a residual plot to understand your data. This is our regression right here. So we're saying, does a change in growth rate predict a change in mortality rate? And what we see is yes, as we see growth rate increase, we also see an increase in mortality. And what we can assess using both visual and mathematical means is we can assess the residuals of each of these data points. And we can say, okay, how big are these residuals? And do these residuals change across our data set? So what we do is we basically take this and flip it, take this line, and put that at 0. So if all of our data points were 100% explained by this line, each of our data points would sit exactly on this 0, on this horizontal line, and each residual would be 0. But we see that's not true because there is deviation. And like I said, the amount of deviation is one thing, but also the consistency of that deviation is another. And what we see is, in this case, we have expanding or increasing residuals, which means that we have some sort of unknown pattern in our data that we have not accounted for. This kind of situation here is something that should give you pause as a researcher to take a look back and say, okay, what's going on? Just a couple examples to kind of bring this around of how you can incorporate this idea of slope, this R, and this idea of R squared. So in this upper left, we both have no slope, and none of that slope is explained by our data. So here, you could very well have a horizontal line, but each of those data points would be on that line, in which case the R squared would be 1 with an R of 0. In this upper right corner, we have a R of 1, so a 1-to-1 ratio, and an R squared value of 1, meaning that this relationship, there is a positive relationship here, and 100% of that relationship is explained by this line. What you'll see as you start working with regressions is that there is there's an infinite number of ways in which you can combine your rho value and your r squared value. And it's just up to you to determine what this relationship means as a scientist for whatever system you're working in. One big note of caution as you go forward. When we're working with our data, we are pretty much bound by what we collected. In this case, this is looking at the number of, this graph on the left here was looking at the number of desert fish species in pools. And this is the area of the pool in square meters, and this is the number of different species found in that pool. Basically, extrapolation will get you into a world of trouble in no time. Extrapolation it's something we tend to, because we want our conclusions to be grander. We often want to make great statements about what our data actually mean. But the most powerful thing you can do as a scientist is make clear statements about what it is that you found, and just what you found, not what you think you could find in the future. So, for an example, in this graph, there seems to be a positive relationship, a positive regression, positive relationship between the area of a pool and the number of species that you would find in said pool. So, if you stumble across a pool of 5,000 square meters in the desert without having looked at the number of fish in there, you could predict that pool would probably have anywhere between 3 and 4 species of fish in it, which is helpful if you're some sort of ecologist doing surveys and you're doing pool study. You're just like studying the presence or absence of pools. Then you could collect data on the presence of species in those pools without actually having to get in there and do the work, because there's a known relationship between area of pool and number of species. But we've only collected data up to about 8,000 square meters and up to 5 fish species. If you were to, say, extrapolate this out to 50,000 square meters, just kept pushing this line further and further and further, then if you got to a pool the size of 50,000 meters, that line would predict a presence of 20 fish species in that pool. Now, that might be possible, but also you might be pushing way past any sort of ecological range that is actually present. Maybe there aren't even 20 fish species in the entire desert. Maybe there are only 6. And so therefore any sort of extrapolation that you would make based on the size of this new pool you found would make absolutely no sense. So this is just another thing to keep in mind as you are working through your data and maybe coming up against the ambiguity, or it's kind of the subjective nature of how we interpret these objective results. And it's important, like in my experience, it's really important to just stick with what you know and be confident in what you found, so that you can stand firmly on your conclusions and back them up without any sort of hesitation. Because this is your world right here. This is your confidence right here. Anything outside of this box is unknown. All right, that's all I've got for you today.